So welcome you back to this module. So last time we introduced the concept of limiting risk efficiency for comparing two different estimators asymptotically. That means as sample size goes to infinity. And we gave the definition of a limiting risk efficiency. Then we developed one result which may be useful in many situations to give you the limiting risk efficiency. Now let me, while we talk about risk, it many times involves movements of sample mean. So what I'll do today is I'll try to give approximations of expressions of sample mean or functions of sample means in terms of their order. Before that, let me just introduce what you mean by your order. So let me give a very crude definition. So suppose Rn is a sequence of real numbers. Now I say that for some alpha not equal to 0, I say that Rn is order of. So this is a big O. There is a concept of a big O. So big order. Rn is big O 1 upon n to power alpha. When I say that, this is equivalent to saying that n to power alpha into Rn is going to some constant C. That is what it means. Now, in the similar fashion, there is a concept of little o or small o n to power alpha. I say that Rn is little o 1 upon n to power alpha if n to power alpha Rn goes to 0 as n goes to infinity. Note that if something is little o 1 upon n to power alpha, it is also little o. If it is little o 1 upon n to power alpha, it is a capital O 1 upon n to power alpha, because this C in that case is 0. So once I have given this definition, now for example 1 upon n plus 1 upon n square. This is big O 1 upon n, because 1 upon n is the order 1 upon n. Because once I multiply it by 1 upon n plus 1 upon n square by n, it goes to 1. It is not of order 1 upon n square, because if I multiply by n square, that goes to infinity, whereas this limit has to be a real number. So let me write down this result. So x1, x2 is a sequence of IID random variables. First part says expected value of x1 is suppose mu. It is finite. Variance of x1 is sigma square. So at a fixed point, so mu is a function of theta, sigma square is a function of theta. It has a third central moment also, so x1 minus mu whole cube suppose is mu3, and expected value of x1 minus mu whole 4 is mu4. So first 4 moments. X bar is 1 upon n summation I is equal to 1 to n xi. So I assume that its first 4 moments are finite. So mu4 belongs to R, that would guarantee that the first 3 moments are also finite. Then what happens? First thing is, what is expected value of x bar? In the case of IID, you know the expected value of x bar is same as the population mean, which is mu. You know what is the variance of x bar, which is expected value of x bar minus mu whole square. this sigma square by n. In fact, which is big O 1 by n. So expect loop of x bar minus mu whole square is nothing but big O 1 by n. What is third central moment? X bar minus mu whole cube. This you know is mu 3 upon n square, which is big O 1 upon n square. Right? It is mu 3 upon n square. Because n square times this goes to mu 3. Expected value of x bar minus mu whole 4, that also you can calculate. That is nothing but mu 4 upon n cube plus 3 n minus 2 upon n cube sigma of 4, which is big O 1 upon n minus 2 n cube. So big O 1 upon n square. So what I see is expected value of x bar minus mu cube is big O 1 upon n square, as well as expected value of x bar minus mu whole 4 is also 1 upon n square. So in general, one can see that if x1 has finite first 2 k moments, if x1 has finite first 2 k moments, the way here x has finite 4 moments, so k was 2 over here, then expected value of x bar minus mu whole to power 2k, so x bar minus mu here 4, would be same as expected value of, so its order, actually the expression would not be same, but their orders would be same. So this is same as order of 1 by n to power k. And expected value of x bar minus mu to power 2k minus 1 would also be of the same order. Let us try to see how do you prove it. The proof is not difficult. Let us see what is x bar minus mu. 1 by n. Summation I is equal to 1 to n xi minus mu. Now this becomes n mu, and then mu you can take inside the sum, so it will become 1 upon n. Summation I is equal to 1 to n xi minus mu. What I can do is you can work out part A, part B I'll tell you, because part B will tell you what is the total, what is the basic argument to get these orders. So x bar minus mu to power twice k is nothing but 1 upon n to power 2k summation I is equal to 1 to n xi minus mu to power 2k. Now, when I am putting xi minus mu to power 2k, what it means? It is x1 minus mu so in general, let us look at if you have expression of the type summation I is equal to 1 to n ai to power 2k. How do you do it? The way to do it, simple combinatorics, I write down a1 plus a2 plus an, a1 plus a2 plus an, a1 plus a2 plus an. 2k times. Now let's try to see. So when I'm taking the product, what is happening is one term is coming from here when I'm considering this product of 2k terms. One term is coming from here, one term is coming from here, one is coming from here. So what is happening? So there is a possibility that from each of these 2k terms, the same term comes. That means a1 comes from each of them. So this will have, then a1 would have a power 2 to power k. So this would have terms of the type ai to power 2k. And there is no choice for me because it is coming from each of them. Then, what is the possibility? ai is coming from 2 to power k minus 1, and from remaining something else is coming. So that means it could be of the top type summation I not equal to j ai to power twice k minus 1 into aj. Now there will be many times, for example, if I am looking at a1 to power 2k minus 1 into a2. a1 is coming from any 2k minus 1, or a2 is coming from any one of them. So what I am doing? I am trying to just see from in how many ways a2 can come. a2 can come from any of the 2k cases, so that would be 2k choose 1. So 2k choose 1, ai 2 to power k minus 1 aj. Okay, then terms could be from 2k minus 2, the same term is coming. So and from remaining 2, the same is coming. So same could be aj square. So from 2k minus 2, ai is coming, and from so in this case I have to choose only choices for from where this aj is coming. aj can come from any of these 2k places, so that would be 2k choose 2. Once the place for aj is defined, from the remaining ais are coming, so I don't have to bother about it. Okay. Now there is also a possibility that from 2k minus 2, the same ai is coming. From the remaining 2, the 2 different are coming. So there will be a term of aj and ak. So plus I not equal to j not equal to k, ai to power 2k minus 2, aj and ak. How do I do that? First I choose, so one way to do it is, first I choose choice for aj. That can happen in 2k choose 1 phase. Now once that has happened, I choose choice for k. Remaining positions are 2k minus 1. So 2k minus 1 choose 1. Once aj and ak are chosen, from remaining ais are coming. So this would be this. Now this can keep on going. One scenario could be from each of them only different things are coming. So there will be ai1, ai2, ai2k. That will be the last term. But before that, what may happen is there may be a term of the type from each ai is coming twice with a power. So a1 square, a2 square, and how many? Only 2k could come, right? So a1 is coming twice time, a2 is coming twice time, and so on. So what could be? No, n is very large. So what may happen is a1 ai, so a1 square, a2 square, the powers can go at the most sum is 2k. And so that means k of them have a power square. So ai1 square, ai2 square, and aik square, right? So k of them, 2, so that becomes 2a power. So 2k powers are coming. So I write down this as different summation I1 not equal to I2 not equal to Ik. So what I have to do? This would be, what will be the coefficient over here? First I choose from which two positions ai1 is coming. So I have to choose 2k, choose 2. Once I have done that, ai2, for ai2 I have to choose two positions. It can come from the remaining 2k minus 2. Then finally 4 choose 2, and it is not 1. So this is what it is. So this would be the situation. Now note that when this happens, there will be of the type, these type of terms. Now aj would be xj minus mu. So it would be xi minus mu to power 2k minus 1, xj minus mu. But xi's are IID. So when I take the expectation, it would be expected of xi minus mu to power 2k minus 1 and expected of xj minus mu. But expected of xj minus mu is 0. So all the terms where only single aij's would be coming, where ai is xi minus mu, would get 0. So what do you get from here? So you get, so I just put, so what I am doing is here is I am putting here ai as xi minus mu. Now if that happens, then expected value of xi minus mu is 0. So here I first put ai is xi minus mu, 0. So then whenever I am taking expectation, this term would get 0, this will not vanish, and so on. So then what do I get? Expected value of x bar minus mu to power 2k would be how much? 1 upon n to power 2k, and would be expected value of xi minus mu to power 2k. So that is mu 2kth moment n times, because all are IID. Expected of xi minus mu to power 2k, all are IID, so it would be mu 2kth. So mu 2k, so n times mu 2k. K is now depending on n. Okay. What would be this quantity? This would be 0, because expected loop of xi minus mu to power 2k minus 1 into expected loop of xj minus mu, which is 0. Let us look at this quantity. So first 2k choose 2, which is a constant, so I don't care about it as long as it is constant. And then this would be how much? Expected loop of xi minus mu to power 2k minus 2 into expected loop of xj minus mu whole square. Expected loop of xj minus mu whole square is sigma square, or mu 2. This is mu 2k minus 2. And I not equal to j, because they were IID, so all of them would be the same. I not equal to j would give me n into n minus 1. Of mu 2k minus 2 into mu square divided by n to power 2k. All right. Now when I have aj and ak, it would be expected of xi minus to power 2k minus 2, because j and k are different and xij's are IID, that means independent, so it would be expected of xj minus mu into expected value of xk minus mu. So expectation of product would be product of expectation because of independence, so this would also be 0. So note that to begin with, I get a term which is of order 1 upon n to power 2k minus 1. This is n into n minus 1, so n square, this would be of order 1 upon n to power 2k minus 2. The smallest order which I am going to get is this one, because whenever one of them is having a power 1, that is going to be 0. So what is this quantity? plus twice k choose 2 and then this would be how much? There are k of them. Each of them is giving a second movement. So mu 2 to power k. And how many terms would be there? N into n minus 1 into n minus k plus 1. N minus 1, n minus k plus 1. Because each of, when I take the expectation, I1, I2, Ik are different, so xi1 minus mu whole square, xi2 minus mu whole square, xik minus mu whole square. So expectation of this product, but because of independence, expectation of this product would be same as expected value of xi1 minus mu whole square, value of xi2 minus mu whole square, value of xik minus mu whole square. Each of them is mu 2. So that is mu 2 here, mu 2 over here, so mu 2 to power k. And then I1 not equal to I2 not equal to Ik gives me n into n minus 1 into n minus k plus 1. Each of them would be occurring this time divided by n to power k. Sorry, n to power 2k. So what I do? This is of order 1 upon n to power 2k minus 1. This is of order 1 upon n to power 2k minus 2. The smallest is coming from here. This is n to power k, n to power 2k. So this is little o 1 by n to power k. Now, when I do it for 2k minus 1, things would be exactly the same. So I have derived it for x bar minus mu to power 2k. Now, when I do it for 2k minus 1, it would be exactly same. What would happen now here is from each of the 2k minus 1, same is coming. So ai to power 2k minus 1. Then same is coming from 2k minus 2. So 2k minus 2. And only one is different, aj. So this would become 2k minus 1 choose 1. This would be again from 2k minus 3, I am getting the same, and from 2 different same. So this is same as 2k minus 3, sorry, 2k minus 1 choose 2. So I choose for position for j. Then over here, so 2k minus 3, then one different over here, and it becomes 2k minus 1 choose 1. I have chosen position for j, then 2k minus 2 choose 1. So on. And then let us look at this situation. I need not bother in situations where only one power is coming, because expected of xi minus mu is 0. So that means power 1 I need not bother, because there would be a one situation because it is 2k minus 1. So there is a possibility that 2k minus 1 is less is how much 2k minus 2. So there is a possibility from k minus 1, 2 powers are coming, and from 1 only 1 power is coming. But 1 power I need not bother because that is going to vanish. So other possibilities when the only ones are from remaining, what I do is, so there is a possibility that from a third power come. Third power come means from the remaining one, how many of them 2 powers should come? So total is 2k minus 1. So from 2k minus 4, that means k minus 2. So I1, I2, Ik minus 2, and Ik minus 1, I put it here. And from one of them, power 3 comes. So ak minus 1 to power 3. So that would make it how much? 2k minus 4 plus 3. 2k minus 4 powers, 2k minus 4. This is the thing. And then this would be how much? This would be some factor which I need not care about, because it is constant, dk. Because I am finally interested in the orders only. So what does it give you? Now, repeat the same thing. It is now xi minus mu to power 2k minus 1. So that will make it n times mu 2k minus 1 plus 2k minus 1 this I need not bother because this would become 0, x proof xj minus mu. So then 2k minus 1 choose 2. This would become n into n minus 1. And then mu 2k minus 3. Sorry, this would be mu 2. Mu square I had written down. Mu 2. Plus 2k minus 1. Choose 1. Actually, it should be 2. Yeah. No, for j only I am choosing 1. Yeah, then I am keep on going is, then finally I get over here dk multiplied by, how many would be this? I have an n minus 1 and n minus k plus 2 and n to power 2k minus 1. Everywhere it would be n to power 2k minus 1. So what happens? It is 1 upon n to power 2k minus 1, 1 upon n to power 2k minus 3, this will be 2k minus 1. So 1 upon n to power 2k minus 2, 1 upon n to power 2k minus 3. What would be this? How many terms are coming over here? n minus 1, n minus k minus 2. So that means n to power k minus 1. n to power k minus 1 and here 2k minus 1, so that becomes n to power k. So it is again little o1 by n to power k. So that proves that expected value of x bar minus mu to power 2k minus 1 as well as expected value of x bar minus mu to power 2k, both are of order 1 upon n to power k. Derivation is simple, just based on simple combinatorics. If you want to get a more insight into it, I would say that try to work it out for expected value of x bar minus mu cube and expected value of x bar minus mu to power 4. That would give you why these different terms are coming. I have given you a combinatorial argument which is simple to follow, but to get a better insight, those who are not so good in combinatorics, they can try first with x bar minus mu whole cube and x bar minus mu to power whole 4. So this is all where I would stop today. Next time I'll deal with some more expressions which may be useful in comparing the asymptotic risks of different estimators as n goes to infinity. So thank you very much. See you in the next module.